But before I do, I should apologize to everybody because I forgot to do the review yesterday. I'll do it today. I think it works out better also. All right. Good morning, everybody. Let me check the chat thing before I start. All right. Got that covered. All right. Good morning, everybody. Welcome to another overcast but exciting morning of Chem 1105 with your host, me, Dr. White. And we got a busy day ahead of us. Let me remind you, tomorrow will be test number 3. We'll take it in class right after the lab. I will send out the password for test 3. Let me check something while you're all here. All right, I just switched to student view in Blackboard. If you look at assignments, you can see test number 3 is all ready for you to download. There are 2 versions, cleverly named A and B, and the other files which you've seen before, plus a periodic table. And tomorrow at about 10-ish, about 10, give or take a couple of minutes, I will send out the email to you with the password for your version of test number 3. You'll have until 11:30 to take it and upload it as a single PDF file. And let me get out of here. All right. So test number 3 is ready for you to download. Like I said, tomorrow I will be sending out the password so you can take it during class. And let's see, another thing, don't forget lab amnesty. If you don't see a score in Blackboard for a lab and you did it, email it to me. If you don't have the lab, email me and I'll send you a copy of it. So then you can email us that way instead of getting 0. Hold on, let's do this. Instead of getting 0, you can get up to 10 points. And it will help your grade, really. All right, that's next. Don't forget the extra credit project. If you want 10, yes, 10. Oh, I can reuse this. 10 bonus points, do it. Remember, my public service to you is send me the project before you've submitted it. I will check it. And if there's anything wrong, I'll let you know so you can fix it. And if you need any help, email me or come to my office hours. Remember tonight from 5 to 6 p.m. here on Zoom with different login though. I will have my office hour. And if you need help with anything, please stop by. All right, what I'd like to do right now is do the review for test 3. All right, thumbs up, people. You see test 3 review on your screen. Thank you. All right, let's take a look at this. First of all, When we talk about gases, an important measurement is pressure. And 1 torr mercury equals 1 millimeter mercury equals 1 torr. Also, this is a mistake. That should be sorry about that. All right, that should be 760 torr equals 760 millimeters of mercury equal 1 atmosphere. And we'll see in a little while when we go through the problem set how to go from one to the other using your good buddy, your good friend, unit analysis. Next, even though you learned this before, don't forget Kelvin equals degrees C plus 273. Now, there are a number of mathematical relationships that are very important in gases we call laws. One of them is Boyle's law, and that's P1 times V1 equals P2 times V2. P1 is the initial pressure. V1 is the initial volume. P2 is the final pressure, and V2 is the final volume. And you'll see I've already gone through the problem set how to go from solve for either P1, V1, V2, or P2 by getting it alone on one side. Next, I talked about the ideal gas law, PV equal nRT. That's my favorite mathematical equation, mathematical, not chemical, mathematical equation in chemistry, PV equal nRT. P is pressure, but it always has to be in atmospheres. V is volume. It's always got to be in liters. And for my class, if you're given it, it will always be in liters. N is moles, but you're going to get grams because I've never seen a balance of that calculate that does moles. So you're going to have to know how to convert from grams to moles, which we covered yesterday. Look at the video, the beginning of it. T is temperature in Kelvin. You're always going to give in Celsius, and you have to use this formula. Go look at important information. Test number, hold on. I'll have to hit my voicemail. All right. That's 4, should stop. All right. Remember, PV equal nRT. T is in temperature, and you're going to have to convert it from Celsius in Kelvin, from Celsius to Kelvin. Now, common mistake using PV equal nRT, students put the pressure, which will be given either in torr or millimeters of mercury, in as that, not convert to atmospheres. The other thing is they put N as grams and not convert it to, guess what, moles. And finally, they put temperature in degrees C and not convert it to Kelvin. By the way, the universal gas law constant is 0.0821. Remember, this is a calculated number, therefore is 3 significant figures. And don't forget, PV equal nRT tells you in the winter, temperature goes down, therefore pressure goes down. Check your tires. In the summer, temperature goes way up, so PV equal nRT tells you since volume and moles and R are all constant in your tire, the pressure will go up. All right, Dalton's law of partial pressure. The total pressure of a mixture of gases is the sum of the partial pressures. And the partial pressure of a gas is the pressure of that gas if it were alone. In that mixture, what would be its pressure if we're alone? And the sum of those equals the total. All right, now don't forget the boiling point of a liquid is when the vapor pressure of the liquid, that's the gas formed from the bubbles, is equal atmospheric. And you should know The higher the altitude you go on our planet, the lower the atmospheric pressure. Therefore, you need less energy to get that pressure when you heat the liquid, and therefore you have a lower boiling point. So if you go to Kathmandu, which Dr. White will probably never go to, but not that it's bad or anything, this is not my cup of tea. Oh, here's my cup of tea. Oh no, it's terrible humor. Wednesday. Oh, my cup of tea. Never mind. When you go up there, it's a very high altitude. Same thing with Denver. Or if you go to the top of the Himalayas, which is another place I won't go because Dr. White will never do mountain climbing. That's not in my blood or DNA, not my thing. Nothing wrong with it. It's not my thing. When you get that high, the boiling point of liquid is like water is lower because the atmospheric pressure up there is lower. Next, and we'll do it right after this, the solutions problem set. Excuse me. Solutions contain one solvent, and that's the component present in the greatest amount, and all other components are called the solutes. Now, there's an important thing that you think it's a liquid or a solution, but it's not, and that's a colloidal dispersion. And where it differs in, it's not true solution where things are dissolved, but you have very small particles suspended in a liquid. And it's not a solution. And the important thing is, oh, I don't have my flashlights nearby. Hold on. Ta-da! Dr. White is a flashlight fanatic. I have about 25 of different flashlights. If this had sugar in it and didn't have humidity on the condensation, all right, needs a new battery, you can see the light goes through. If this were milk, you wouldn't see it. Why? Because milk is a colloidal dispersion, and the small particles that are not truly dissolved disperses the light and won't let it through. Got to replace the battery in this. Now, important, very important aspect of solutions is the concept like dissolves like. And like solutes are soluble in like solvents, which means polar solvents are solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. And what's polar? Water, salts, like sodium chloride and alcohol, or alcohols. What's nonpolar? Vegetable oil, Vaseline, gasoline, baby oil, and later on we'll learn dirt and grease are also nonpolar. If you mix water and vegetable oil together, it won't mix because one's polar, one's nonpolar, and like dissolves like. Oh, know this. Now, solubility of a solute, that's the maximum amount of solute that will dissolve in a given amount of solvent. Once you reach that, you can't put one molecule more. It will precipitate out. You'll get a solid form. And a saturated solution contains the maximum amount of solute that can be dissolved under the conditions the solution exists. Therefore, same thing, saturated solution. You have a saturated solution. You can't dissolve any more solute in there. It will precipitate out. Now, the opposite of saturated solution is dilute solution. And a dilute solution is a solution that contains a small amount of solute relative to what can dissolve. Now, concentrated contains a lot of solute relative to what you could dissolve, but you're not as saturated. You can still add more, but you got a lot. Now, aqueous means the solvent is water. Water is the solvent. And it's shown by bracket AQ close bracket. And that tells you you have a aqueous solution. Now, there are different ways to make sure that you make the right or same type of solution. And we call that concentration. I talked about concentration by mass and by volume. We won't cover that in test 3 or the final, but we will cover molarity. And molarity, which is shown by capital M of a solution, is a ratio giving the ratio of moles of solute per liter. But because 1 liter equals 1,000 milliliters, this equals that, and that's what we use. Ooh, very important. Know this. Hint, hint. Now, just to remind you, the atomic, 1 mole of an element equals atomic weight in grams, 1 mole of a compound equals molecular weight in grams, and the molecular weight equals the sum of all atomic weights. Now, don't forget, molarity, capital M, is moles of solute per 1,000 milliliters. And we'll go through that in a little while. And remember, there's a certain type of problem where you're given how many grams you need to make so many milliliters of a certain molarity solution, and you need to do 2 steps. The first one is milliliters to moles, and we're going to do that in a practice problem right after this. And the second step is moles to grams, and you get your answer. And that's the review. Any questions? Going once, twice, you know, I was that coordinated 3 times. By the way, I am ambidextrous. I learned how to use a bullwhip with this hand and crack it before I could do it with this one. And same thing, I learned how to throw a boomerang so it'd come back with my left hand before I mastered it with my right. But other things, I'm really right dominant, right hand dominant. Oh, I told you, you learn a lot about Dr. White. Oh, you got to be careful around me. One of my hobbies is unusual weapons, knowing how to use them. Bullwhips, boomerangs, and my favorite, nunchucks. I have 8 pair of nunchucks, but I'm not Bruce Lee. I wish I was. He was awesome. All right, with that, let's do the problem set. But first, let me close something. Oh, I see a request, maybe. All right. All right, thumbs up, people. Well, first of all, let me check. And now it's your turn. Do you see Chapter 5, Part 2, Solutions, Practice Problem on your screen? Thank you. All right, let's go through this. These are things you should know for test number 3. Give an example of a colloidal dispersion that you use in your daily life. And milk is probably a good one. Well, it is. Latex paint. Don't try with the flashlight at home ever, but your blood is a colloidal dispersion, not a solution. And I could also add mayonnaise, ketchup, and mustard to that. Now, give an example of a solution you could use in your daily life. There's a lot of them. Pop is a solution. Remember, I'm from Chicagoland. The stuff in a bottle or can that's got bubbles, carbonated, and non-alcoholic, we call pop, not soda. Did I tell you Werner's is my favorite? Hold on. I don't know if I ever told you this. We got time. All right, everybody, if you need labs, send me an email with the labs you need, and I'll send them back to you later today. Because after class today, I teach another class from roughly 1 o'clock till 4 o'clock. So, anyways, if you need any kind of labs under the amnesty, send me an email. And I was just talking about pop as a solution. And my favorite pop is this right here, Werner's. You can get it at Jewel. Some places you can't, but they always have it at Jewel. It's a very highly carbonated, highly spicy, awesome ginger ale. I've been drinking it for many, many years, and it's good. I also like Dr. Pepper. That's a good one too. Yes, I'm a doctor, and I'm a pepper, a Dr. Pepper. No, oh, like I said earlier, it's totally terrible Wednesday humor. All right, let's look at 3, 4, and 5. They're all the same. If a solution has 12 grams of KBr, potassium bromide, 10 grams of water, what is the solvent? What is the solute of the solution? The component present in the greatest amount is always the solvent. The other components are the solutes. Now, in this one, Dr. White was playing a trick on you. Normally, water is a solvent, but it doesn't have to be. And this one, KBr, would be the solvent, and water would be the solute. If we look at the next one, same question, but different solvent and solute. You have 56 grams of ethanol, 125 grams of water. What's the solvent? What's the solute? And what's present in the greatest amount? Now water is the solvent and ethanol is the solute. Now, what does 1.34 capital M HCl mean? And what it means is capital M is molarity. Therefore, it's 1.34 moles of HCl per 1,000 milliliters. Molarity, moles of solute per 1,000 milliliters of solution. We just don't write the word solution down there because everybody knows that's what it is. And you don't have to do that. And now you know too. And, ooh, And I'll ask you, I assume everybody can see it. Let me check. Yep, you should. What does this mean? 8.95 capital M HBr. Your turn. All right, I'm going to assume everybody's done. And what does that mean? As soon as you see capital M, that's molarity. And that's equal to moles solute per 1,000 milliliters. And therefore, what does this mean? 8.95 moles HBr, because that's the solute. What's after the M, capital M, is the solute per 1,000 milliliters of solution. Now, if you look at number 7, what does, and you got to look hard, but is, I see a question possibly. All right. Question was asked of me, and I'll put it on my whiteboard right now. Let's call this A. Let's do a B, and you can do this too. Don't forget, please pass the Nacl, sodium chloride table salt. What does that mean? All right, time's up. Capital M. As soon as you see that, it means molarity, which means this. Therefore, what does this mean? 3.55 moles of sodium chloride per 1,000 milliliters. Now, I mentioned earlier in the review, and let's take a look at it. What does 4.56 times 10 to the third capital M NaCl bracket AQ close bracket mean? And what is the solvent of the solution? First of all, capital M, molarity, moles per thousand, moles solute per thousand milliliters. Therefore, 4.56 times 10 to the third moles of sodium chloride per thousand milliliters. Now, what's the solvent? AQ in a bracket stands for aqua, water. That means the solvent is water. Now, since you know molarity is moles per thousand milliliters, let's look at number 8. And number 8 is how many moles of sodium chloride are 125 milliliters of a 3.45 capital M NaCl solution. What are we being asked to find? How many moles of NaCl, moles of NaCl? We're given 125 milliliters of solution, and we're given this 3.45 capital M NaCl. What does capital M mean? Molarity, moles of solute per 1,000 milliliters. And therefore, what this really means is 3.45 moles of sodium chloride per 1,000 milliliters. Now, the only number we have to really start with is 125. What units do we want our answer in? Moles of sodium chloride. And that's what I have a ratio and times 125, what milliliters, what units do I want? Milliliters of NaCl. And guess what time it is? You're right. It's time for your good buddy, your good friend, unit analysis. I'll throw in another one. And unit analysis, whatever you're trying to get to goes on top of the ratio, moles of NaCl. Whatever we're trying to get rid of goes underneath, milliliters. Where do we get these numbers? From knowing that this number, 3.45 capital M NaCl, is really moles of sodium chloride per 1,000 milliliters, which we put in. Now, the 1,000 is an exact number, and it plays no role in number of significant figures. Therefore, this is 3, this is 3, my answer is 3. Remember on test 3, just like 2, underneath your name, it will say, first of all, please use proper significant figures for all calculated answers. And second, it will say, please use 3 significant figures for all atomic weights. And like test number 2, if you don't, I take off a point. KOH is potassium hydroxide. And the question is, 8 points, how many moles KOH, and it could be 6 too, 6 to 8, depending on my mood. I'm being honest with you. How many moles of KOH are in 822 milliliters of a 1.111 capital M NaOH solution? Let's do this stepwise. Your turn. Just put, what are you being asked to find? What are you given? And also, what does something might mean? Your turn. Do that first. All right, let's take a look at it. What are we being asked to find? How many moles of KOH? Potassium hydroxide. What are we given? We have 822 milliliters of the solution, and this number, 1.111 capital M KOH. And as soon as I see capital M, I know that's molarity. And what does this mean? I'll give you a chance to do it. Your turn. What is that? 1.111 capital M KOH mean? Time's up. Capital M molarity. That's 1.111 moles of solute, in this case, the solute is KOH, per 1,000 milliliters. Now, the only number we have to work with is that. And hold on while I check my chat request. Dina, I'll get back to you at the end of class on that question of yours, okay? So what do we have? The only number we have is this. And if we have some ratio, what do we get? I'm going to let you figure out what's the answer here, or not answer, units, and what units go up and on top and below that ratio. Use your good buddy, your good friend unit analysis. Not asking you to calculate anything, just put in the units, which is why this is called unit analysis. Your good buddy, your good friend. Anybody keep count of how many times I say that? Because I am going for the Guinness Book of World Records, saying that the most time in a summer semester. All right, time's up. What are we trying to get to? Units, moles. Let me write a better mole. Moles of KOH. What goes up here and here? Well, you use your good buddy, your good friend, your analysis. Whatever I'm trying to get to goes there. Whatever I'm trying to get rid of goes there, unit-wise. And now I'll write that. And where do I get a ratio or relationship of moles of KOH to milliliters? Right here. 1.111 moles of KOH per 1,000 milliliters. Now remember, this is an exact number. This is 4 significant figures. This is 3 significant figures. Therefore, my answer, when you do multiplication or division, you get the same number of significant figures in your answer as the answer to as the number you're multiplying or dividing as the fewest, which is 3. So my answer will be 3 significant figures. Now, before I pick up my calculator, I'm going to check. Notice milliliters divided by milliliters cancels out because A divided by A equals the number 1, cancels out. I'm left with moles of KOH. Guess what? I think this is going to come out all right. And now I'll turn on my calculator, clear it. And my calculator gives me the following number. And that's not 3 significant figures. Why don't you round it off, and then I'll show you how to round it off to 3 significant figures. Time's up. Keep the 9, keep the 1, keep the 3. Use the 2 to round off. Is that 4 or less? Yes. So I'm going to drop all that. And the correct answer is 9.13 times 10 to the minus 1 moles KOH. Which just reminds me, it's time for a special, very special public service announcement from your host, me, Dr. White. Hold on. Special announcement. Remember on test 3, show your work. If you make a math error, like push the wrong buttons and you get the wrong number, if you show nothing, I give you 0 points. If you show your work and I say, oh, you made a math error, and say we're 10 or 15 points, hint, hint, wink, wink, say no more, guess what? You'll get Either if it's 10, you'll get 9 points. I'll only take 1 point off for math there. If it's 15 points, you'll get 14 points. But if you don't show your work, you don't get any partial credit. So it's in your benefit. Ooh, is it polite to point? Your benefit. I said it's awful humor Wednesday to show your work. Do it. It's in your benefit. All right. And if you notice, I have a number of problems like this that you can go back in your leisure time and practice. But now let's look at number 11. And thumbs up, people. Everybody see number 11 on their screen? Thank you. All right. Now, the question is, how many grams of sodium chloride are needed to make 345 milliliters of a 6.789 capital M NaCl solution, salt solution? So the question is, what are you being asked to find? Grams of sodium chloride. What are you given? Well, the volume of solution you need to make, and this number 6.789 capital M NaCl. Capital M, you know, means molarity. And what does that really mean? 6.789 moles of sodium chloride per 1,000 milliliters. Now, I like to do that immediately whenever I see that because I know I'm going to need it in the form I have underneath right here. Now, there's no way you can go directly in one step from milliliters to grams. You need 2 steps. And let me open up something for you. And everybody see on your, well, maybe you don't. And you don't. Everybody see on your screen molarity and then molarity 2-step? Thank you. This is an important information. Test number 3, molarity 2-step. Step 1, we go mils to moles. Step 2, moles to grams. We just did number 1. Yesterday we did number 2, beginning of the lecture when I did a review of going from moles to grams and grams to moles. Go back and look at the video. I can say that. Or come to my office hour. That's not what I want. So, first step, milliliters. We want to go to moles of sodium chloride, use unit analysis. Whatever we're trying to get to goes on top of that ratio. Whatever we're trying to get rid of goes underneath. And where do we get the numbers? Moles of sodium chloride per milliliters from the molarity, 6.789 moles of sodium chloride per 1,000 milliliters. And remember, 1,000 milliliters is an exact number, so I have 3 and 4. My answer should have 3 significant figures. And notice milliliters divided by milliliters cancels out. I'm left with moles of sodium chloride, which I want as my final answer. Am I done? No, I want grams of sodium chloride. And that's one of the advantages of writing out what you're trying to find and the units, because you can say, am I done? No, I already know what I have to get to, and that's not it. So now we do step 2. Step 2 is moles of whatever you calculated to grams. Here we have 2.34 moles of sodium chloride. We want to go to grams of sodium chloride. You use unit analysis. Grams of sodium chloride goes on top of this ratio. Moles of sodium chloride go underneath. Where do we get that information for that ratio? you look at important information, test number 3, 1 mole of a compound equals its molecular weight of that compound in grams, and the molecular weight of the compound is the sum of all atomic weights. So I have to get the sum of all atomic weights first. And I don't think you saw that. Now you see it. Important information you have, and it'll be at the end of your test. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. So now I need the molecular weight of sodium chloride, the 3 significant figures, the atomic weight of sodium, there's only one of them, so I can put it down, 23.0. There's only one chlorine. Chlorine atomic weight, the 3 significant figures, is 35.5. Add it up. Remember, when you do addition, you have the same number of significant figures to the right of the decimal as the number that has the fewest to the right of the decimal. And that would be 1. So 58.5 is correct. And 1 mole of a compound equals its molecular weight. Moles divided by moles cancel out. We're left with grams. Remember, the number 1 is an exact number. And don't forget, 2.34 is 3 significant figures. 58.5 is 3, and my answer is 3 significant figures, 137. Now notice I have on there both ways. And as I've said many times, there's 2 philosophies when you're doing a series of multiplication divisions like we are here. One is you round off at each step, which is what Dr. White, me, likes to do. The other is rounding off at the end, which I don't like to do. However, I will not force you to do the way I do it. And what that means is you can round off at the end or at each step, and I'll calculate both for test number 3 answers when that situation exists. And the key here, first of all, is understanding that there's no way you can go directly from milliliters to grams. You can't. Therefore, when you can't do that, guess what? You need more than one step. And for this problem, you need 2 steps, which is conveniently found in important information. You need 2 steps, and I show you the 2 steps, milliliters to moles and moles to grams. And if you notice, I give you a couple more to try and work out yourself. And when we come back from our break, which it is time just about within about 20, 30 seconds, we'll do one together. And with that, let's take a break. I'll see you in about 5 minutes. Ooh, 5 minutes exactly. Do I time things good or don't I? Don't answer that. But anyways, I'll see you in 5 minutes at 9:55. Take a break because I'm going to do some stretching. Oh no, I'm running late. All right, quick question before, and I can use the poll. Just dawned on me. Now, the question will say, are you done? But just think a yes or no. Can you hear the fan over my shoulder? Yes, you can. No, you can't. I don't have my hearing aids and I've got about a 50% loss hearing in both. So I can't hear it, but you may. Do you hear it in the background, my fan? Instead of saying, are you done? Answer yes, you can, or no, you can't. And I've got to launch the poll. There we go. All right, let's try this. It's not that warm today. Now, using yes or no, does it sound better now? Yes, with the fan off, or no difference? All right, it's sort of most of you no difference, but I'll leave it off. All right, let's get back to work. And now we're going to do another fading prompts, which I call winky dink problem, where we're going to do it step by step. And let's look at the following problem. And make sure you can look at the following problem. Yep, you should be able to. All right, question is, and thumbs up people, can you see it on your screen? 10 points. Thank you. All right, how many grams, that's what G stands for, NaOH, sodium hydroxide, are needed to make 333 milliliters of a 4.4 capital M NaOH solution? What I'd like you to do first is, what are you being asked to find? What are you given? And maybe, what does something mean? Your turn, do that first. All right, time's up. What are we being asked to find? How many grams NaOH? So grams NaOH. And I use the question mark to let me know that's what I'm trying to find. What are you given? We have 333 milliliters of solution, and we're given this number with a capital M and then NaOH. And immediately when I see capital M, I ask the question, what does that mean? And it means 4.44 moles NaOH per 1,000 milliliters. And now I look, I'm trying to go from milliliters to grams, and I can't do that in one step. You need 2 steps. And important information will tell you step number 1, you go from milliliters to moles. And step 2, you go from moles to grams. And in this case, it's the solute, whatever you're trying to find. And we're talking about NaOH. So let's do step 1. And I'll help you out. And you fill in all the rest. Just put the numbers. You don't have to do the actual calculation. Put everything in what units you want to solve for. I'm really fading prompts now. And I'm talking about just this first step, putting in stuff to help solve it. All right, let's do it. It's time to use your good buddy, your good friend, unit analysis. We had a ratio. We want to convert milliliters to what? Moles. Moles of sodium hydroxide. And how do we proceed? Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of this unit ratio. Whatever we're trying to get rid of goes underneath. It's moles of NaOH per milliliters. And where do we get these numbers? From here. Knowing that the molarity, this, means this, we know is 4.44 moles of NaOH per 1,000 milliliters. Now, I'm going to come back and, well, let me do it now. Because I do it both ways, I'm going to open up my Bill Gates calculator, otherwise known as my spreadsheet. If I can move it. And over here, I'll have plus 333 milliliters times 4.44 divided by 1,000. And my spreadsheet gives me 1.47852. I don't know if everybody can see this. And the answer is no. Now you can. And if I round this off to 3 significant figures, that'd be 1.48. And now I'm ready for step number 2. And you might have seen this as 1.478, whatever, times 10 to the 0. Remember, 10 to the 0 equals the number 1. So that's why I can write this as 3 significant figures. Now we've done step 1, it's time to do step 2. Step 2 is moles to grams. And I'll help you out. Plus, I'll help you out. One more play. The atomic weights of sodium to 3 significant figure atomic weight is 23.0, oxygen 16.0, hydrogen 1.01. And why don't you fill in the rest here and here? Your turn. All right, let's do this. How do we do this? Well, we're trying to go from moles to grams, and therefore we want grams of NaOH. What do we put here and here? Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. I'm having a bad arrow day, real bad arrow day. Let's redo this. That's better. And therefore, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And that's grams of NaOH per moles NaOH. And where do I get those numbers? Remember, 1 mole of a compound equals its molecular weight. And the molecular weight is the sum of all atomic weights. And if we look in important information, test number 3, which you should be able to see on your screen right now, that 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. And you would have to look it up, but being the nice person I am about to sneeze, so hold on. I think I stifled it. Anyways, here are the atomic weights. I'll add it up. When you're adding, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest, 1, 1, 2. Keep the 0, use that to round off. It's 4 or less, I'll drop it. So for every 1 mole, you have 40.0 grams of sodium hydroxide. And moles divided by moles cancel out, because anything divided by itself equals the number 1, meaning it's gone. Left with the right units. Notice this is 3 significant figures. 3 significant figures. The 1 is an exact number and doesn't play a role in significant figures. So my answer should have 3 significant figures. And now I can go to my calculator, or in this case, my spreadsheet. And if you notice, this time we get a difference. If you do it at the very end, you get 5 5.91 times 10 to the first. If you do it the other way, it's 5.92 times 10 to the first. Therefore, on a test, both answer would be correct. And that's how you do it. And with that, we're done with the problem set. Does anybody have any questions about anything dealing with solutions or with test number 3? Yep, I got my speakers on. When I first started doing Zoom, I forget to turn, I have 2 big speakers and I forgot to turn them on. And I can't hear you. And I realized, oh, I have to turn my speakers on. Duh. All right. Well, in that case, let's move on to material that will be on test number 4, which is coming up soon. Let me close a few things here. All right, we're talking about acids and bases. Don't forget, and let me check first. All right, thumbs up, people. Can you see Arrhenius acid and base theory on your screen? Thank you. And you don't have to know this, but you should know hydrochloric acid, the structure of that is HCl, sulfuric is H2SO4, and nitric is HNO3. You don't have to know the structure of acetic acid, but you should be familiar that in water we call vinegar. Now, when I say you should know this, you should know these structures are acids. And hydrochloric acid, HCl, your body makes for your stomach. Bases, sodium hydroxide, potassium hydroxide, ammonia, and sodium bicarbonate. And you should know those are bases. And we went through all this. And for the Bronsted-Lowry theory of acid and base, since Arrhenius doesn't explain what happens in non-aqueous solutions, that's when water is not the solvent. Bronsted and Lowry independently, and that's why it's named after both of them, came up with a theory, and an acid is a proton donor. And you should know this. That's why it's in red. If you haven't figured out, red's my favorite color. When it's in red, that means it's important. And acid is a proton donor, the proton H+. A base is a proton acceptor. That means it accepts H+. And if we look at water, if you add an acid to it, H+, you'll form the hydronium ion, which is what I have there. But I'll talk about a little later. Today I'll do it. Bronsted-Lowry, you could take HCl and ammonia, which neither have water, and you'd form the ammonium and chloride ions, and that is that space. All right, let's get back to work. This is new stuff. Switches on. There's something called conjugate acid, conjugate base pairs, and the proton transfer does not occur at 100%. That's just an equilibrium show. It goes this way, and this reaction goes this way. And that's called an equilibrium. In this class, unlike Chem 1211, I don't teach equilibrium as a separate chapter, which I do in the other class. But still, it's good to know that what this means. Now, in chemistry with acids and bases, we have what's called conjugate acid base. And a conjugate of a species is when you have two species chemicals that differ by only one proton, they're called conjugates. One is the conjugate of the other. Now here, I'll rewrite this. HA is an acid, B is a base. Now, let's look at the conjugates. And I'm going to go Technicolor on you. And I just did a generation gap. When movies first came out in color, I was a little kid. They were made a big issue. Oh, and living color and Technicolor. Now, notice HA and A minus. It only differs by H plus. Now, students have a hard time seeing this. I'm being honest with you. So a way to do this is just look at H. If two things differ by H, hydrogen, which is really H plus, they're conjugates, and that makes your life easier. So HA and H and A minus differ from H, actually H plus, but for you, so they're conjugates, and that's why I drew a line connecting them. Now, HB and HB also differ by H plus, but just think of H, and they're conjugates. Now, if we were to label this and the question is, label the conjugates and the acids and bases. Now, W, when it goes from W to Y, does it lose a proton? For you, think of H. Does it lose or gain an H? And the answer is it loses or donates H and a hydrogen, a proton, and that makes it an acid. Now, X, when it goes to Z, does it gain H, really H plus, or lose H? And the answer is it accepts or gains H. And a proton, something that accepts a proton, is a base. Now, by convention, this side is always called the conjugate, which I'll abbreviate like this way. Therefore, X, Y, and Z are called the conjugates of A and B, or HA and B. So let's look at Y. Why not? Oh, it's really humor day. Anyways, let's look at Y. And when it goes from A minus to HA, which means going this direction, does it gain or lose a proton? Think of H. And the answer is it gains a H or proton. What's something that accepts or gains? That's called a base. So Y is called the conjugate base. Next, let's look at Z. When Z goes this way, it goes from Z to X. Does it gain or lose a proton, donate a proton? And think of hydrogen. One hydrogen, no hydrogen. It lost it. It donated a proton. What's something that donates a proton? An acid. And because it's on this side, it's called the conjugate. And that's how you do it. Let's look at a real life one. Now, the first thing I would ask you to try and do is draw a line, or in your mind, what are the two conjugate pairs? Something that differs by a hydrogen. Hint, look for each side that has the same type of other atom or element besides hydrogen. Time's up. Let's call this W, X, Y, Z. And one thing I should mention, there's no convention which is acid or base first, but anyway, students think so, and there isn't. Let's look at W. What's on this side, the right, that has a chlorine? And it's Y. And so notice when you go from W to Y, you've lost a proton, differed by a proton. Now, let's look at X, ammonia, and it goes to what else has a nitrogen? Z. So notice X and Z, ammonia, NH3, and ammonium cation, NH4 plus, only differ by a proton. So they're conjugates. And we'll try one where you'll do it. But if I ask, what is the acid and base? What is the conjugate acid? What's the conjugate base? By convention, on this side, the right side, those are always the conjugate, always. Now, if we look at W, when it goes to its conjugate, Y, does it gain a hydrogen, really a proton, but it's easier for you to think of H, or lose it? One hydrogen, no hydrogen. It lost a proton or donated. What's a proton donor? An acid. Now, when Y goes back to W, does it lose or gain a proton? Here it has none, here it has one. Count the hydrogen, it's easier for you. And it's gained a proton or hydrogen. What's something that accepts or gains a proton? And that's a base. But because it's on this side, it's called the conjugate base. All right, let's look at X. And it goes to its conjugate Z. It has nitrogen with 3 hydrogen, goes nitrogen with 4 hydrogens and a plus charge. Does it gain or lose a proton? Count hydrogens, H. Goes from 3 to 4, it gains. What is something that gains or accepts protons? A base. Now, going from Z to X, do you lose or gain a proton? Count hydrogens, 4 to 3. Oh, you lost one. What's something that loses or donates protons? An acid. Therefore, W is the acid, X is a base, Y is a conjugate base, Z is a conjugate acid. and focus on this, why don't you try identify the acid and base and conjugate acid and base in this reaction? Your turn. All right, let's do this. If we look at nitrogen, this has a nitrogen. So these are conjugates. They differ by one proton. This has one, this has none. So when we go from W to Y, do we lose a hydrogen, a proton, look at the H, or gain it? And the answer is we lose or donate it. That's, hold on, wrong color, right color. That's an acid. When we go back, Y to W, it's conjugate. Do we gain or lose a proton? Think of hydrogen. Here we have none. Here we have one. We've gained or accepted it. Remember, on this side, both Y and Z are by convention conjugates. And therefore, when Y gains a proton, accepts it, it's a base, and it's on the right, makes it a conjugate base. Now we have, what's the conjugate of X? Potassium hydroxide, water. Notice, forget about the potassium, one hydrogen or two, it actually picked up a proton, but for you it's easier, count hydrogens. What's something that accepts a proton? A base. Wrong color again, sorry. And when it goes from Z to X, does it lose or gain a proton? Think hydrogen. 2 to 1, it lost or donated it. What's something that donates a proton? An acid. And therefore, that's a conjugate acid. And that's how you do conjugates, and you should know how to do this. And here I have the conjugate base of an acid, the species that remains when an acid loses a proton, and the conjugate base of an conjugate acid of a base is called the conjugate acid, is the species formed when a base accepts a proton. Well, we've already done the examples. Now, I'm switching the switch. Will this be on a test or the final? Click to the off position. Now, acids have different strengths, and so do bases. Now, there's strong acids, and that means in the equilibrium, to lose a proton, it's almost 100% that side. And I don't have the equilibrium equation, but that's it. And strong acids are these examples, when HCl, HBr, HI, also nitric acid and sulfuric acid. They're very dangerous too if you don't watch out. Now, a weak acid, again, is something that transfers only a small amount, like 5%. An example would this be acetic acid. Now, I'm going to do some organic chemistry because I'm an organic chemist. That's the acidic proton. And very little goes to this side, and that makes acetic acid a weak acid, which in water, 5% of this makes it a very weak acid, because if it was a strong acid, you'd be dead or in the hospital. You're not. So that's a weak acid. Now, the same thing, strong bases. That's a base that really wants your proton. And when you have bases that are formed MOH, where M can be sodium, potassium, or lithium for the most part, those are very strong bases. Now, a weak base is sodium bicarbonate. And sodium bicarbonate, you should remember, is a base that's found in baking powder and baking soda also. Now, conjugate bases, strong acids are weak bases, switches off. The following is probably going to be some of the most important things I'll ever teach you this semester. Pay attention, please. Ooh, I know what I can do. Did I get your attention? We talked about this a little yesterday when I had to zoom ahead, but water is amazing stuff. And water can react with itself, and it's called dissociation of water. And one water molecule gives up a proton, the other accepts it. Now, this little arrow tells you not much goes to this way. Most of it stays like this. That's why we have the big arrow. But a little can, and what it forms is H3L plus, the hydronium ion, and OH minus hydroxide. And this happens in anything where there's water, like your blood or your stomach. Anywhere there's water, this is happening. In my bottle of water. Now, there's a mathematical way of determining certain constant for equilibrium reaction. And for water, that's called Kw, named after Dr. White, Kenneth White. No, not really, I wish it was, but it isn't. It's called the ionization constant for water, or the water equilibrium constant. K stands for constant. And what's that equal to? The concentration, and this in a bracket means moles per 1,000 milliliters or per liter. And the concentration of the hydronium ion concentration times the hydroxide equals 1, or really 1.0 times 10 to the minus 14. And this is for water at room temperature. And for most things in our daily life, this works well. Now, you should know this equation. I used to have students have to memorize it, but in test 4, you'll be given this. Now, when you have an acidic solution, the hydronium ion concentration is greater than the hydroxide. And that's an acidic solution. And if you probably heard, well, let me ask everybody, let me do a, hold on one second. Let me do a full view. How many of you have heard that, oh, let's do this even better, put you all on the spot. How many of you heard that your stomach contents is acidic? Give me a thumbs up. A couple of you know. Your stomach is, oh, more than a couple, is acidic because you have, and this is one of the miracles of life for me personally, I think of, cells that make an acid. And having an acid present makes the hydronium ion concentration higher than the hydroxide. Now, for a basic solution, this is stuff you should know. For a basic solution, the hydroxide is greater than the hydronium. And we call this a basic solution. And sometimes it's called alkaline. And batteries used to be acidic. The batteries you put like in a flashlight or your car, others, well, that's still acidic. But in the flashlight and your cell phone and all those, and now the batteries you normally put in a flashlight are called alkaline batteries because inside the battery, the hydroxide concentration is greater than the hydronium. And finally, we have a neutral solution, and that's when hydroxide equals hydronium, H3O is hydronium, and actually it's ion, and OH is the hydroxide anion or ion. Anion means negative, cation positive. All right, let's have a little fun with this one. Oh, my initials. And let's look at the following, which is something you need to know how to do. Before I do that, oh no, well, let's do this one. We'll have time. We may go a minute over our break time, but you'll still get your full break. Thumbs up, people. Do you see what is the OH3 plus in brackets? Thank you. All right, let's look at the following. What is the hydronium ion concentration, H3O plus, if hydroxide is this? Well, how do you do that? What are we being asked to find? This. What are we given? What are we also given? This. So how do I solve for this? I want to solve for hydronium, therefore I need to get it alone on one side. How do I get rid of hydroxide? I divide this side by hydroxide OH minus, because anything divided by itself is the number one. Whatever I do to one side, I have to do to the other. And notice hydroxide divided by itself, anything divided by itself equals the number one, cancels out. And I'm left with and how do I calculate this? Here's hydroxide number. I'm going to put that in. Put this in my calculator and I get 1.0 times 10 to the minus 10. And that's how you calculate hydroxide. If I look at the clock, oh no, it's time for a break. I'll see you in 5, which is 10:50. Take a break, because I am. I'll see you in 5. Nope, I didn't get lost. I was trying to get something on the internet for you. All right, let's get back to work. But before we do, public service announcement from your host, me, Dr. White. Don't forget, tomorrow after the lab, I will be sending out the password for test number 3. You'll have until 11:30 to take it and upload it unless you've contacted me for reasons that I allowed you to be late. And also that includes, and nobody raised their hand or say anything now, if you have a letter from the Center of Access and Accountability, uh, accommodations, I'll get it right, 1 year. Uh, you like test 1, remember the email I sent you about extra time. And with that, I better get to work. All right. Now, when it comes to calculating or considering acidic, basic, or neutral solution, looking at the hydronium ion concentration, hydroxide, better yet, let me back up one step. And let's you try one. And why don't you try this one on your own? And then I'll do it. If the hydroxide ion concentration, OH minus, equals 1.0 times 10 to the minus 10, by the way, that's moles per liter, but nobody ever writes that down, as I just didn't, then what is the hydronium ion concentration? H3O plus. And I give you KW, yay, that's me knows that. But anyways, H3O plus concentration times OH minus concentration equals 1.0 times 10 to the minus 14. Why don't you try and solve for H3O plus? And you don't have to calculate it, just set it up. And when you're done, give me a thumbs up. Remember, anything divided by itself is the number 1 and it's gone. Give you another 30 seconds. In the old days, we'd say the clock is ticking, but my computer doesn't tick or talk. Look out, it's generating beyond Awful Humor Wednesday. All right, time's up. Let's get to work. And the question is, what are you being asked to find? And the answer is right here. We're trying to find H3O plus. What are we given? The hydroxide is ion concentration 1.0 times 10 to the minus 10. And we're also given this, that the hydronium ion concentration, H3O plus, times hydroxide ion concentration equals 1.0 times 10 to the minus 14th. Now, if we're going to solve for this, we need it alone on one side. How do we do that? Well, first of all, we move the screen, come on screen, up a little, give us more room. Well, if I want to have this alone, I have to get rid of that. How do I do that? Well, when you're multiplying things, you can divide. And that would be anything divided by itself equals the number one. Whatever I do to one side, I have to do to the other. And I did. This becomes one. So 1 times hydronium ion concentration, H3O plus, equals this. And the other side is still this. Now, what's hydroxide? Well, I figured that out from the problem right there, so I can put that number in. And if I do the math, which this one I can do in my head, but that's because of my slide rule experience, the answer is this. And that's how you do this. Now, when we talk about acids and bases or acidity and basicity, remember for solutions, and we're talking about aqueous solution, meaning water is a solvent, acidic solution is this, basic solution, also called alkali, is this, and neutral solution is this. In case you forgot, this math symbol means greater than. Well, if you look at the problem we just did, is this acidic or basic solution? Well, here's the hydronium, here's the hydroxide. I got to think about that. That's hurt my brain. Not really, but the hydronium is greater, but it's hard to tell. You got to think about it. Well, it turns out chemists came up with an idea to make it simpler for you, and that we call pH. And the pH concept involves the pH scale. This is scale of, hold on, I've got to shut down Word and start it again. Sorry. Well, I lost some of it. All right, I think we're back to where I was. When I do too much writing on tablets, sometimes that happens. I haven't figured it out yet. All right, let's check. Thumbs up, people. You see pH constant on your screen. Thank you, Ashley. And let's take a look. pH is a scale of small numbers that specifies the hydronium ion concentration. How do you calculate it? And by the way, time to be very, very subtle. When I was a student, if I put in the left margin a couple of stars, it meant it was important. If I put a couple of stars in the word letters IMP, I knew I better know this for the test. And this is what I'm writing for you. The pH, by definition, is minus the log of the hydronium ion concentration. And the pH, if my gift to you, if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x, which another way of saying it is pH equal minus the log, and that's logarithm power of 10, then the pH is x. So this is the pH scale, or pH, how to calculate it. Now, you should know pH ranges from 0 to 14, never less than 0, never more than 14. The lower the pH, the more acidic a solution is, the higher the pH, the more basic. Now, important thing, note this is a logarithmic scale. Logarithmic means going from 5 to 6, they differ by 1 power of 10. 5 to 7, that's 100. So it's powers of 10. And let's go to my wrong thing. This is something you should know. Hold on. All right. Why are you being... All right. Sorry about that. All right, let me just confirm. Everybody see pH on your screen? Thank you. You should know this. pH 7, that's neutral pH. Less than 7, the solution is acidic. Greater than 7, it's basic. The closer to 0, the more acidic. The closer to 14, the more basic. Now, this is the pH scale. And let's look at, I sort of showed this to you yesterday. Well, let's go through it again. I found a nicer one. Everybody see the pH scale on your screen with the pretty pictures and the colors? Thank you. Now, if you notice vinegar, which is acidic because it's less than 7, has a pH of 3. Now, battery, what they're really talking about is sulfuric acid, that's in your car battery, has a pH 0. Your stomach acid by this chart is 1. Now, if we go to the other side, drain cleaner, some of them are acidic, is a pH 14, very basic. Now, baking powder, which is a weak base, has a pH of 9. Now, I'm going to argue with this where they say 8. Let's look at something. pH of blood is usually about 7. I might be wrong. Well, I was pretty right. pH of blood is about 7.35 to 7.45. If it's beyond that range, you're dead. You're going to have serious problems. And the pH of your blood is very important. Now, can everybody still see the pretty pictures? And water, if it's totally pure, is pH 7. You're not going to find the water coming out of your tap being totally pure to be pH 7. An ammonia solution, like for cleaning your windows and stuff, is pH 11. So the higher you go in the scale, the more basic it is, or alkaline. The lower you go, below 7, the more acidic it is. And they don't have on here, let's do one thing while I've got the pH of lemon juice is about 2. It's acidic. Things that are acidic, acids that you can actually taste, are very sour. How many of you have ever bit into a lemon? Ooh, it's really sour. Or had very strong lemonade? That's because it has an acid in it called citric acid, which is a weak acid, but still your tongue and brain says, ooh, that's sour. Lemons have a little less citric acid, so they're not as sour as limes, but they still got a kick to it. You go, ooh, it's good to put in different dishes, limes and lemons too. And most things that are acidic that you can taste are sour. How many of you have ever tasted vinegar? It's sour. And I don't think you're going to do shots of vinegar. No, it's sour. Now, I have never really tasted it, but bases have a more bitter taste to it as opposed to sour. So let's do pH practice time, because it's probably one of the most important concepts, pH. For those of you who have a swimming pool, you know you have to keep the pH of the water at a certain level. Otherwise, it causes eye and skin irritation. When I moved into the house I have now, there was above ground pool, which took me about 2 years to realize I'm not a pool person. And it's a lot of work adjusting the pH and making sure it's proper. You have to measure it. Now, all right, got it. All right, can everybody see the problem? If the hydronium ion concentration H3O plus is equal to 1.0 times 10 to the minus fifth, by the way, I didn't see anybody had their thumb up or I missed it. Can you see the problem? Thumbs up, people. Thank you. If the hydronium ion concentration H3O plus equal to 1.0 times 10 to the minus fifth, then what is the pH of this solution? And is it acidic, basic, or neutral? So what are we being asked to find? pH. What are we given? By the way, it's always lower p, capital H, lowercase p. We're given the hydronium ion concentration. And you will be given an important information. I used to make students memorize this. The pH is equal to the hydronium ion concentration. And if it's if the pH is 1.0 times 10 to the minus x, then the pH or the hydronium is this, the pH is x. So how do we do pH? I'll put it in because I have the hydronium ion concentration. And what is the pH? Well, X is 5, so the pH is 5. Now the question is it acidic, basic, or neutral? How do you do that? Well, let me remind you, and this you have to memorize. If the pH is less than 7, it's acidic. If it's equal to 7, it's neutral. More than 7, it's basic. And therefore, I hope you all agree, 5 is less than 7. So this is an acidic solution. And it's time for you to try one. I'm going to try an experiment. Nope, that isn't going to work. I tried something that didn't work. I'll write it. And let me remind you, and it's your turn. 5 points. If H3O plus hydronium ion concentration equals 1.0 times 10 to the minus 10, then what is the pH of the solution? And is it acidic, basic, or neutral? By the way, 10 to the C divided by 10 to the D equals 10 to the C minus D. And it's your turn. While you're doing that, I'm going to get some more water because I'm running out of water. I'll be right back. I'm back. All right, time's up. Let's do this. What are you being asked to find? pH. What are you given? What are you also going to be given? This. And therefore, pH equals minus the log of the hydronium ion concentration equals minus the log, which we have right here, the hydronium concentration, 1.0 times 10 to the minus 10. When this x, 10 to the minus x, when this is 1.0, the pH is x. In this case, x is 10. Now the question is it acidic, neutral, or basic? First of all, this is our pH, and you should know When you have pH 7, it's neutral. When it's below 7, the pH, it's acidic. And finally, when it's above 7, it's basic. And the answer here is it's basic. Now, let's do one more problem. Eh, 7 or 8 points, depending on my mood. I could put down is this acidic, basic, or neutral, but let's just do this. And the question is, what is the pH if a hydroxide ion concentration is 1.0 times 10 to the minus fifth? Well, what are we trying to find? pH. What are we given? Hydroxide OH minus 1.0 times 10 to the minus fifth. And remember, pH equals minus the log of the hydronium ion concentration. Uh-oh, we don't have this, but wait. Kw, not me, but I wish it was, equals the hydronium ion concentration times the hydroxide equals 1.0 times 10 to the minus 14. So you need 2 steps. In step 1, we will find or determine the hydronium ion concentration. And let's do that. Well, we're given this. Does this look familiar? Yes, we just did something like this. And we want to solve for this. So how do we get rid of this? We divide by that. Because anything divided by itself equals the number 1, not 0, 1. Because A divided by A equals 1. Whatever you do to one side, you have to do the other side. This cancels out. We're left with the hydronium ion concentration equals 1.0 times 10 to the minus 14th divided by hydroxide ion concentration. What's hydroxide? Oh, it's 1.0 times 10 to the minus fifth. So I'm going to put that in there. And this equals 1.0 times 10 to the minus 9. Are we done? No. This is the hydronium ion concentration. We've been asked to find the pH. So now we have to do step number 2. And that will be determine or calculate the pH. And pH equals minus the log of the hydronium ion concentration, which we just figured out right here. So that's equal minus the log of 1.0 times 10 to the minus 9, which is equal to 9. And that's how you do it. Let's go through this again. you're being asked to determine what is the pH of a solution. I could have written down if OH minus concentration hydroxide is equal to this, 1.0 times 10 to the minus fifth. So we did this, and remember, log pH is minus the log of the hydronium ion concentration. We don't have it, but we know, and you'll be given this also on test number 4, important information. The hydronium ion concentration times the hydroxide equals 1.0 times 10 to the minus 14. You need 2 steps. Step 1, find the hydronium ion concentration, and you use this equation. You solve for H3O plus concentration by dividing one side by hydroxide and the other. Anything divided by itself becomes number 1 and is canceled out. And you're left with this. I put in this number, I get this number, which is equal to this. And now I do step 2, pH equals minus the log of the hydronium ion concentration. It should be H3O plus. And I put that in because we just calculated it. And remember, when this is 1.0 times 10 to the minus x, the minus log of that number is x, when this case is 9. And that's how you do it. Now, we're going to come back to that problem probably either tomorrow or next Monday. Oh, I'd like to move on and talk about a couple important things that I should mention now. Everybody see my whiteboard? Thank you. 2 days later, I'll be done. What happens then? Oops, hang in there. I just forgot. Oh, come on. So let's look at the following. Everybody can see this. I'll read it to you. What happens to the numerical value of the pH of a beaker of water at pH 7.0 if I add a few drops of H2SO4? And let me write over here because you can't see it. Now, you have to know, first of all, H2SO4 is an acid. And when you add an acid, it becomes more acidic. But I'm asking you what happens to the numerical value of the pH, and it will go down. So the answer here is it decreases. Or you could put an arrow, goes down. So whenever you add an acid to something, the pH value will decrease. It becomes more acidic. Now, whenever you add NaOH, what is that? It's a base. And you should know NaOH is a base. And whenever you add more base to something, it becomes more basic. Now, I'm not asking you what has become acidic or basic. I'm asking what happens to the numerical value. And in this case, when it becomes more basic, the pH will increase. It goes up. So you should know when you add an acid to something, and there are a couple of acids you should know the formula of. H2SO4 is one, HCl is another, HNO3 is the third. And that causes the pH to decrease the number. Now, when you add a base like NaOH, KOH, or ammonia, NH3, the pH will increase because it becomes more basic. Acid, decrease in pH, base, increase. If I look at the clock, our time together is almost gone. Boy, time flies when you're having fun with acids and bases and other things like molarity. But anyways, remember tomorrow morning, we'll do the lab. I have to post it later today. It will be a Beyond Lab Z. And afterwards, take about an hour and 15 minutes, because I got to teach you something I didn't get to today called titrations. And we'll cover that tomorrow morning, because you'll need that not only for the course, but also for the lab. Next, at about 10-ish or so, I'll finish by 10, I better finish. I will send out the password for test number 3. If you have any questions about anything on test number 3, the labs or anything else, come to my office hour tonight from 5 to 6 p.m. on Zoom, not this one, the other one. You have that in your syllabus. And don't forget to study. I'll be posting this video later today. And with that, don't forget, hand in the lab that's due tomorrow. And if you have any outstanding labs that haven't been graded, make sure you email me with the labs, or if you need the labs, email me and tell me, hey, I need a copy of that lab, and I'll send it back to you. With that, I'm going to say, Gang gesund. Bye. I'll see you tomorrow.